Hi. So last time we made pretty general consideration of a system of capacitors, or basically a system of metallic islands, each of which can be regarded as a capacitor with some capacitance, and uh, and each island is hooked up to some potential source so that they can be separately set at its own potential. And then we claimed that there was this relation connecting the charge at each conductor, Qi, as a function of the potentials in at every other conducting islands. And I claimed that this relation is a pretty general one. So today we're going to make a pragmatic and concrete application of that idea, and trying to find a solution to the following problem, the following question. So the question is the following. Here we have two infinitely large capacitor plates, and they're both grounded, which means that their potentials are both set to zero. Um, and then you insert some point charge somewhere in the middle between the two plates at a distance z0 from one of the plates. Now, this charge Q will probably induce some charges on both sides of the plates, denoted by QL and QR. And the question is just exactly how much charge is going to get induced on each plate. And separation between the plates is set to be D, and the separation from one of the plates to the point charge is set to be Z0. So that's the setup of the problem, and the question is whether we can find the exact amount of induced charges, QL and QR, as a function of the point charge Q. Um, I mean, frankly, this is a pretty baffling problem at first, unless you know exactly how to attack this problem. Um, First of all, let's think about the physical situation. So there will be some electric field lines emanating from this charge, and then they will probably terminate on the surface of these metallic plates. Um, and then by integrating these field lines backward from zero, because that's the potential of this plate, by integrating the field lines backwards down to the location of the point charge, you can infer that there must be some finite potential, electrostatic potential, associated with the location of the charge little q. Um, so that's that's something of an obvious statement, except that we don't know exactly what would be the value of this potential. Um, However, that's not what we're interested in after all. Well, we are interested more in the amount of induced charges, QL and QR. And we still haven't made any progress regarding the way in which to compute these induced charges. So, what should we do? Well, I mean, the first obvious approach may be that the since we had this general formula relating the charge on each conducting island in terms of the potentials of all the metallic islands, maybe we can just apply that formula and see what happens. Um, well, let's see. Well, we have one conductor over here with the charge QL and potential zero. And then we have another metallic island over here with charge QR and potential 0. And we can certainly think of this as a small metallic sphere with charge little q and some potential phi. Okay, then we can just apply this general relation in this context, denoting 1 for the plate on the left, and then 2 for this little spherical ball of charge, and 3 for the plate on the right. Okay, then the relation will read like QL will be proportional to the potential at phi 0 at Z0 multiplied by the value of the mutual capacitance C12. And all the other terms in the general equation will be 0 because the potentials on both of these metallic plates are by definition 0. And you can write down a similar relationship for QR as some coefficient multiplying the potential at the position of the little metallic sphere. Okay, so that's something you can write down immediately, but okay, sorry, I forgot. There's also an equation for the Q, which is given by the potential itself multiplied by the self-capacitance C22. But okay, so we managed to set up these equations in a rather short amount of time, but it's not really helping very much toward the solution because we don't really know what these all these capacitances are, C22, C32, C12. We don't really have any idea what exactly are these values. So we need some additional information. And then I first tried to find a detour by thinking about the situation without this extra charge in the middle, but simply with some accumulated charge QL and QR on either side of the plates, and then maybe thinking about the electric field which is created by such a charge distribution, and then perhaps then superimpose this presence of this extra charge and so on. So I struggled with this idea for about an hour. And then I had to admit that this is really a dead end and nothing in the way of progress can be made along this line of thinking. So it's sometimes the case, especially in many problems of electrostatics, that sometimes a clever idea is the only way to proceed effectively. And I think this is just one of those instances where a more straightforward linear approach will not take us anywhere, but rather using a trick can go a long way and give us the solution in a rather simple manner. And so the trick I'm going to be talking about from now on depends on this thing called the Green's reciprocity theorem. I mentioned this theorem actually early on in my lecture, but presumably you forgot all about it. And certainly I forgot all about it. So I want to repeat that statement of what the Green's reciprocity theorem is. So as an example, I want to consider this situation where you have two chunks of charge distributions. And they don't really have to be conductors. They can be just any kind of charged matter. And then you think about the total electrostatic potential of this combined system. So the first chunk is characterized by the charge density rho 1, and the second chunk of matter is characterized by the charge density rho 2. And the electrostatic energy for the whole system is like this. If you think about this from the perspective of rho 2, it's the rho 2 multiplied by the potential and this potential is coming from these other charge distribution rho 1. So the phi 1 can be written as this integral. And then by inserting this expression, you find that this electrostatic potential energy is given in this pretty symmetric manner as a product of two charge densities divided by the separation. But once you have this symmetric expression at your disposal, you realize that you can kind of switch partners. And then first take out this factor rho 1 like this. And then express everything else as a potential phi 2, where phi 2 is now given by this integral here. So we have this two equivalent ways of expressing the same energy, which is an integral of rho 2 and phi 1, or an integral of rho 1 and multiplied by phi 2. So electropotential energy computed in either one of these ways is obviously the same, as we have just proven. Okay, so that was the statement of the Green's reciprocity theorem. But how do we apply that exactly to the situation consisting of n conductors? That's not that obvious at first sight, but first, let me restate the Green's reciprocity theorem, not in the way that I have originally stated 2 minutes ago, but in a different way. Okay, it turns out that this second way of stating the Green's reciprocity theorem is a far more useful way and actually help us toward solving the problem I proposed at the beginning of the lecture. Okay, so here we go. So we're given this situation with a bunch of conductors. Well, again, it doesn't really have to be a bunch of conductors. It can be any number of chunks of matter consisting of some charge density function rho r. And this charge density will give rise to some sort of potential distribution phi r. And given these information, we can obviously compute the electrostatic energy. However, now, given the same chunk of matter, so you don't change the shape of each one, you don't change the shape of any of these materials, nor the locations of any of these materials, but what you do change is the potential distribution. Okay, so it's the same shape and location of the materials, but endowed with a pretty different kind of charge distribution. All right, and obviously that will lead to a pretty different kind of potential distribution. So I'm going to use a prime to denote a new potential and the new charge. Now, it's very obvious that these old distribution of charge And the new distribution of charge will have a very different amount of electrostatic energy, right? This integral has no reason to be equal or to this integral because they correspond to completely different charge distribution. However, now comes the important point. Now, instead of taking the product of the charge density with the corresponding potential, we can sort of take the cross product of the old charge density with the new potential and integrate over all space and compare that value to the product of the new charge distribution multiplied by the old potential integrated over all space. And it turns out that these two integrals are exactly the same no matter what we choose for the new charge density rho prime and the new potential phi prime. And the proof is as simple as can be as can be imaginable. The reason is that the new potential phi prime is given in terms of the new charge density rho prime in this familiar manner. And now we use this formula to express the rho times phi prime like this. Okay, and as in the previous proof of Green's reciprocity theorem, I'm going to switch partners and isolate rho prime first. If I isolate rho prime out like this, then the remainder is this function. But this function is nothing but the potential generated by the old charge density rho. So I'm going to call it phi. So now the integral has a new expression as the integral over the product of rho prime and phi. So we begin with the expression which is an integral of rho and phi prime, but turns out that's equivalent to the integral of rho prime and phi. Okay, so this is probably simplest possible proof of any formula in physics that are actually useful. Now, when you apply this conclusion to the situation consisting of a set of conductors, then and then remembering that the potential, every piece of conductor is an equipotential and characterized by a single potential value, which is phi I for the conductor labeled I. Okay, and then this reciprocity relation tells us that if we are given an old distribution of potentials and charges and a completely different distribution of potentials and charges like this, then their cross product, like this, is equal to this cross product. Okay, and this is not very intuitive, but not all valid proofs have to be intuitive, as we have just shown. This is obviously true. So we can just keep on using this fact and explore some interesting consequences. For example, the new charges Q prime I is related to the new potential phi prime through the capacitance matrix like this, just as the old charge Qi is related to the old potential phi through the same capacitance matrix. And they are the same capacitance matrices because, as I said earlier, neither the shape nor the locations of these conductors have changed between the old configuration and the new configuration. And Cij being a purely geometrical quantity cannot have changed in the process. Okay, so when we insert these two expressions for q prime and q back into this formula, we find that there's this equivalence between this expression and this expression. And by comparing the first expression with the last expression, you see that the only thing that changed was this Cij became Cji. Okay? But this relation better hold for any choice of phi I and phi prime j. And the only way for that to hold is if we require that these capacitance matrices be strictly symmetric to begin with. And in the previous lecture, I kind of stated this thing without proof, without giving you the proof. But now here, this is the proof. And the proof is heavily dependent on the clever use of the Green's reciprocity theorem. So being clever not always helps us in making progress in physics, but in this case, it's really helpful in carrying us to the next level. Okay, so how this Green's reciprocity theorem would apply to help us find the induced charge QL and QR. Okay, so now we need to address this question directly. And invoking Green's theorem, we just write, we can just write down this this relation without really knowing what that would really mean. Okay, so here we have a bunch of unprimed variables. And the variables without the prime refers to the actual charges and actual potentials in the actual situation we have in mind. And the prime quantities refer to the charges and potentials for the hypothetical situation that we have not yet specified. And the beauty of this approach is that we can choose the hypothetical situation in whatever way we want, as long as it helps us find the solution to the question we are asking. Okay, so here's the thing. We don't really know what this phi z0 potential value is, but rather than working our sweats off to find out what this value is, we just find a trick to not to have to consider this value. And that's by considering a hypothetical situation where q prime is 0. That is, in our hypothetical situation, we don't put any charge whatsoever in the middle. In other words, we don't consider the case we're going to consider will not have any charge in the middle between a pair of capacitors. Okay, so by assuming such a hypothetical situation, we can nicely get rid of this term that contains the information that we are not able to provide. And therefore, our equation becomes simpler, like this. But wait, actually, we can make this even simpler, because in the real setup that we had in mind, both of these plates, metallic plates, are grounded. So that means phi L is 0 and phi R is 0. So everything on the left-hand side is 0. Okay, so now we have an even simpler equation to deal with, like this. Okay, so this is a product of some actual charges, QL, QR, and little q. and some hypothetical potentials, phi L prime, phi R prime, and phi Z0 prime. Now it's time for us to finally choose a concrete hypothetical situation. And the situation we will choose is, for example, like this. One of the plates is set at zero potential. The other plate is set at potential V. And of course, there's no other charge in the middle because we took the Q prime to be zero in our hypothetical world. But this is a situation where we know how to solve the problem very well. Potential simply increases linearly from 0 to V as a function of distance, which means that the hypothetical potential phi prime is simply given like this. So the hypothetical potential phi prime is pretty easy to solve in our hypothetical situation. So we take advantage of that and insert various results for phi L prime, phi R prime, and phi prime Z0. And the result is this. Now this trivially gives us the induced charge QR in terms of the charge we have placed in the middle between the capacitors. And that's nicely proportional to the separation, to the distance, relative distance that the charge is located with respect to the one of the plates. Okay, so that's the result. That's the correct result. Now we can get QL by using a similar but slightly different hypothetical configuration, namely where the left side, where the plate on the left side is set at potential V and the plate on the right is set at potential 0. Now in this case, the hypothetical potential at location Z0 is obviously given by this function, and therefore our Green's reciprocity relation will read like this, and therefore the induced charge QL will be like this. Okay? So in a very trivial way, once we know how to use the right trick, we can obtain the answers to the questions we asked without taking too much sweat. So this is like, playing magic or card trick. Once you know exactly what tricks to play, the rest of the actual solution is pretty straightforward and easy. Okay, thank you for listening.